Hello, this is Dr. Baxley. This is a mini lecture on electrolysis, an important topic in the electrochemistry chapter. In electrolysis, an electric current is generated in a power supply or in a battery, and that's used to push electrons in a non-spontaneous direction. Electrolysis is a really useful technique for a number of different things. Electrolysis can be used for electroplating, which is the process of reducing a substance from its ions onto another metal surface. For example, in this diagram, a piece of zinc, the anode, is being oxidized. Electrons are transferring from the left side to the right side. As the zinc electrode on the left is being oxidized, it will form some zinc 2 plus ions in solution. The zinc 2 plus ions can then be reduced onto the iron surface. Normally, the zinc ions wouldn't have a high enough reduction potential to reduce into iron, but with the electrochemical power supply, the power source up here at the top, that can drive the reaction to go in a non-spontaneous direction. This is useful because now a coating of very durable and rust-resistant zinc can be plated on top of a piece of iron. This is how galvanization works. Electrolysis can also be used in the purification of metals. For example, some copper solid can be oxidized with a power supply into copper 2 plus ions. The copper 2 plus ions can then migrate to another electrode made of copper, and the power supply can force the reduction of the copper 2 plus ions back onto a different piece of copper. There's a great figure in your book you can check out. It's also possible to prepare hydrogen gas via electrolysis, where an electric current just gets run through an electrolyte solution, often of sulfuric acid, and hydrogen forms as a result. There's some important parts of electrolysis. One is that oxidation always occurs at the anode. This is the same as in all other electrochemical cells, like the galvanic or voltaic cells that you did in lab this week. Another important part about electrolysis is that the anode is always considered positive, which is the opposite sign as in voltaic cells. You'll see those labeled as negative. There's some relationships you can use for electrolysis. This is the first relationship, in that the moles of electrons and the moles of reactants or products can be related to each other stoichiometrically. An example is the electrolysis of sulfuric acid solutions, where 2 electrons would combine with 2 protons to make one H2 molecule. So there's a stoichiometric relationship between the electrons and the H+, or the electrons and the H2 molecules. Another relationship is that an amp is equal to 1 coulomb per 1 second. Or, if you rearrange that equation, 1 coulomb is equal to an amp times a second. This equation or relationship will help you relate coulombs, or amount of charge, to current and seconds. So it gives us a way to talk about moles at one point with coulombs and Faraday's constant, and time. Another way of saying this is that current times time equals charge. One last relationship is Faraday's constant. And Faraday's constant, of course, is that 1 mole of electrons is equal to 96,485 coulombs. This ratio can be used in stoichiometry to relate moles of electrons to coulombs. And since we have another relationship of coulombs or charge per time, eventually one can relate time to moles of electrons or moles of a reactant or product. Let's take a look at this first question. The first question asks about the mass of chromium that can be plated from a solution of chromium 3 plus with a certain current in a certain amount of time. Let's work backwards a little bit. If we knew the number of moles of chromium, it would be possible to calculate mass of chromium. We could get moles of chromium 3 or chromium metal from moles of electrons, knowing the half reaction that would occur to get chromium metal out of chromium 3 plus. Now the trick would just be able to figure out how one could calculate moles of electrons from the information given. Is it possible to do that from the time and current information given? It sure is. We can start with the 16 amps of current, multiply it by the time in seconds, and then we can multiply it by the relationship that 1 amp second is equal to 1 coulomb. We also know that there are 96,485 coulombs in every 1 mole of electrons. In the half reaction, 3 moles of electrons would have to combine with 1 mole of chromium 3 plus in order to make 1 mole of chromium metal. The chromium metal has a molar mass of 52.00 grams for every 1 mole, so this works out to be 10.3 grams of chromium metal that can be plated out. I had to edit this question just a little bit. You might have noticed that one version of the printable lecture notes had a time involved. So in order to reduce 42.3 grams of titanium-4 to titanium-2 with a certain amount of current, we might start at the beginning of this problem. We might be able to calculate from mass of titanium, moles of titanium, and that would be titanium-4+. Knowing it takes 2 electrons to do that reduction, we could calculate the number of moles of electrons needed. Once we know moles of electrons, we might be able to use Faraday's constant. And at the end of the problem, we might be able to use the relationship of amps, seconds, and coulombs to calculate time in seconds. So let's see how that works. So up to this point, we've been able to calculate moles of electrons needed to react with a certain mass of titanium-4+. Faraday's constant can then be used. Once the number of coulombs are used, that can be related to amp seconds. Since we're looking for time, and we know the number of amp seconds, if we divide through by the current, that will let us calculate the number of seconds, which would end up being 45,471, or that would work out to be 12.6 hours. So there's a brief introduction to electrolysis.